The Unit 4 review video for part 1. I'm going to break this up. There's 42 review questions. I'm going to break this up into 2 parts. So I'm going to do the first 21 questions in this video and the second 21 questions in the next video. All right, so let's try number 1. So number 1 and the first, I think 4 of them are related rate problems. This is telling us that we have a cone and we're looking at the volume of that cone. And we want to find the rate of change of the volume of the cone with respect to time. Now, the first thing I noticed with my volume equation here was I've got some stuff that is a constant, like 1/3 in pi, but I have other stuff that's not. So to make this a little easier for me, because I do have to take the derivative eventually, is I'm going to distribute r squared times 10 minus r to get 10 r squared minus r cubed. Okay, so now when I find the derivative, I'm going to do dv over dt, that's the derivative. I'm going to bring this 1/3 pi in front, and then take the derivative of 10r squared minus r cubed. All right, so again, my 1/3 pi is just a constant. And then this becomes the derivative of 10r squared is 20r, and then minus 3r squared. But don't forget, like when we did this in our very first lesson for this unit, you also have to write dr over dt. So we're trying to find the rate of change of the volume. So we're trying to find this. It tells us that our radius is, it doesn't tell us radius, so let's just leave r alone. But it does tell us that our radius is changing. The radius of the cone is changing with respect to time. That's 6, so times 6. So whatever this is will give us our answer. So 6 times 1/3, or 6 divided by 3 is 2. So this is 2 pi times 20r minus 3r squared. If I distribute again, I get 40 pi r minus 6 pi r squared. So if you look at the answer choices, the answer choice is E. All right, that's the first one. All right, let's go number 2. Number 2, we have a triangle where theta is increasing at a constant rate of 3 radians per minute. At what rate is the side length x increasing in units per minute when that side length is equal to 3 units? All right, so what I first noticed about this is that I have to come up with some type of equation that relates all this together. And I have a right triangle, so I'm thinking about SOHCAHTOA here. And if I use the sine of theta, right, so the sine of theta, that's equal to the opposite side over the hypotenuse. Okay, so now I'm going to differentiate. The derivative of sine is cosine. Okay, so I know I need to do that. And then we have times d theta over dt, because that's the rate at which the theta is changing, equals, now if you think of differentiating, I'll do it over here, right, ddt of x over 5, the way that I would do that really is differentiating 1/5 times x. All right, and if you differentiate 1/5 times x, that's just going to give you 1/5. So that's equal to 1/5, but don't forget we do something else there. We have dx over dt. All right, now we're trying to find the rate at which x is increasing in units per minute. So we're trying to find, I'll highlight my unknown here, trying to find dx over dt. But here's the thing, we have too many unknowns right now because we do know that our theta is increasing at 3. So this is going to be times 3. And we're trying to find dx over dt. But we need to find the cosine of theta. All right, so if this x is equal to 3 units, right, it tells us x equals 3 units. And this is a right triangle. And I know with the Pythagorean theorem, I mean, I know this because this is one of those special ones. But this side length has to be 4. But if you don't know that, you could do 3 squared plus your question mark squared equals 5 squared. So that's 25 minus 9, which is 16. So our question mark is 4. All right. So the cosine of theta is adjacent over hypotenuse. So that's going to be 4/5 over here. Okay. So now I'm just solving here. I have 12/5 equals 1/5 times dx over dt. If I move the 1/5 over by multiplying by 5, that gives me just 12. All right, so that's the rate at which x is increasing in units per minute when the side length for that is equal to 3 units. Okay, let's go to number 3. Very similar problem here. We have the radius of a sphere is decreasing. That's a key thing we haven't seen yet in any of these problems. So make sure when you plug in that 2, you make it a negative because it's decreasing. And we want to know at the instant when the radius of the sphere is 3 centimeters, what is the rate of change of the surface area of the sphere? So I have surface area equals 4 pi r squared, okay? And we're trying to find the rate of change in the surface area. So this is going to be ds over dt. That's what we're trying to find. Similar to what we did in the previous one, my constants 4 pi don't change, but then we do need to multiply by 2r. That's the derivative of r squared, and then times dr over dt. So I'm solving for that rate of change in the surface area. So 4 pi times 2 times our radius is 3 centimeters. Now watch this. The radius of the sphere is decreasing at a rate. So this, when I plug in that 2, make sure it's a negative 2 for the dr over dt. So whatever this is our answer. We have 8 times 3 is 24, times 2 is 48, so negative 48 pi. So C. Okay, let's go number 4. This is going to be the last one, number 4, on related rates. We have the base of a triangle is increasing at a rate of 3 inches per minute, while its height is decreasing at a rate of 3 inches per minute. So remember, one's going to be positive, one's going to be negative. Which of the following must be true about the area of the triangle? Well, let's write down the formula for the area of a triangle, which is 1/2 times base times height. Now watch what happens when I differentiate this. I'm going to do dA over dt. We know we have the 1/2 times. Now I need to differentiate, so ddt of base times height. So this is going to be one of those problems where if you don't know your differentiation rules, it becomes difficult. So this is going to be the product rule. The derivative of b is going to be 1 dB over dt, then times the original height, plus derivative of h, which is 1 dH over dt times the original base, and that's equal to the change in the area of the triangle with respect to time. All right, so I can clean this up a little bit. So 1/2 times, let's plug in what we know. The base of the triangle is increasing at a rate of 3 inches per minute, so that's 3h. All right, and then plus the height is decreasing at a rate of 3 inches per minute, so that's going to be negative 3b. All right, if you want to write it a little different, you can. So that's 3h minus 3b. All right, we're trying to figure out what's happening to our area with respect to time. All right, well, let's see here. Let's just plug in some numbers. So I'll try if b equals 1 and h equals 2. If I plug that in, I get 3 times 2, which is 6, and then 3 times b of 1 is 3, so that's going to be a positive. So dA over dt is positive. Let's change it up this time. Let's make b equal to 2 and h equal to 1. All right, so this time I have 3 minus 6, which is a negative. So that's going to be a negative. So let's look at our answer choices here. Well, it's not always increasing or decreasing, right? Because that depends on what we use for our base and our height. All right, and then it doesn't remain constant. It is changing. So we're only focused on the decreasing answer choices here for C and D, and that looks like that's this one here when it's a negative. So that's when your base is greater than your height. So when your base is greater than your height. So that's going to be 4 is D. Okay, let's go number 5. Now, with the next few, we're going to be moving to the next lesson, which was on linear approximation. Okay, so if you need to refer to your notes, go to 4.2 for that. And I'll show you what I'm writing down here from that. I'm writing down this right here, formula to help me find this stuff. So the linear approximation for a value, so that's equal to f of a plus f prime of a times x minus a. Okay, so it says we're trying to find the linear approximation, all right, of a zero of our function. And we're trying to find what that approximation is. So this is a tricky one. I'm already kind of starting off pretty tough here, but you're actually trying to solve for x. And the linear approximation for that x is actually 0, right? It says to find a 0. So f of 3 is 2. Let me plug it in so we can show all the steps here. All right, so let's plug in what we know. F of 3 is 2. F prime of 3 is 5. All right, and we're subtracting x minus, because we're trying to find x minus that 3, because we're using the tangent line to the graph at x equals 3. So now it becomes actually just algebra 1. So this is 2 plus 5x minus 15. If I move over my non-variable stuff, I get a negative 2 when I go over there and a positive 15, so that's going to be 13. All right, so whatever 13/5 is, let's see what 13/5 is. 2.6. All right, so that's number 5. Number 5 is C. Let's go number 6. All right, we have g of 3 is 2, and g prime of 3 is negative 3/4. They're telling us that the graph of g is concave down. I'll go over what that means a little bit later, on the interval between 2 and 4. Which of the following is true about the approximation for g of 2.6 using the tangent line to the graph at x equals 3? So I'm going to use that same formula again. Let me do it over here. So we have L of x equals f of a plus f prime of a times x minus a. So we're trying to find the approximation for 2.6. All right, so that's going to be f of 3 plus f prime of 3 times 2.6 minus 3. All right, so that's going to be f of 3. I guess I wrote f, should have written g, my bad. G of 3 is 2 plus g prime of 3 is negative 3/4 times negative 0.4. All right, so let's see what we get for our answer here. It's going to give us half of the answer. So we have 0.4 times 0.75. They're both negative, so it becomes a positive, plus 2, which is 2.3. All right, so I know that my approximation is 2.3. All right, now let me show you how I get the answer here. So first thing I do is I draw a sketch. Okay, they're telling us g of 3 is 2. So I'm going to go over 3 units and up 2 units. There's 3, 2. Okay, and we're approximating at g of 2.6 is 2.3. So g of 2.6 is 2.3. So like there. Something like that. Okay, you don't have to label it. Now they're telling us that this is concave down. Okay, the graph is concave down for this. So when we do concave down, right, I always think of concave down, you have to think of a frown. All right, so a concave down, when you're connecting these, right, should look like a frown. All right, and if it was concave up, you're thinking that it is like a cup, it can hold water. Okay, so when I look at this, what it creates, right, it looks like it's overestimating it, because when we create that concave down, it's a little bit higher. So that's why it's an overestimation for number 6. Okay, let's try number 7. Okay, number 7 says that we're trying to find the linear approximation for g of 4.2. So I'm going to do g of 4.2 equals g of 4. All right, we're using x equals 4 for our tangent line here. All right, or where the tangent line, the point at which the line is tangent to the graph, plus g prime of 4 times 4.2 minus 4. All right, we know g of 4 is 12. G prime of 4 is 2.2, and that's going to be times 0.2. So whatever this is the linear approximation for 4.2. So this is like kind of the most basic version of how I could ask this question. All right, using the calculator, we get 12.44, or A. Let's try number 8. Last one for approximations here. We have a function, 2 cosine of x plus 1. What is the approximation for f of 1.5 found by using the line tangent to the graph of f at x equals pi over 2? Well, the first thing I notice is that we don't know what our what happens when we plug in our x value of 1.5. All right. I'm sorry, we don't know that. We're trying to approximate it. But what I meant to say is we don't know what happens when we plug in an x value of pi over 2. So I'm going to plug in pi over 2 because I'm going to need that. So 2 cosine of pi over 2 plus 1. Now, pi over 2 is a quadrantal. So if you forgot your quadrantals, please use that formula sheet from trig. All right, but pi over 2 is at 0, 1. All right, and cosine of that would be 0. All right, so 0 times 2 is 0. 0 plus 1 is 1. So that's going to be f of pi over 2. So for the linear approximation of 1.5, I'm doing f of pi over 2, right? I'm using this as the point at which my line is tangent to the graph, plus f prime of pi over 2 times 1.5 minus pi over 2. All right, now there's one more piece of information I need, and that's the evaluating the derivative of my function at pi over 2. So let's find, let me do a little sidebar here. Let's find the derivative of 2 cosine of x plus 1, right, that function. All right, again, 2 is a constant, so it's just going to come down. Derivative of cosine is negative sine, so it's going to be negative 2 times the sine of x. Derivative of 1 is just 0. So I want to evaluate, this is the derivative. I'm going to evaluate the derivative at pi over 2. Okay, quadrantal again. Sine of pi over 2 is actually 1. 1 times negative 2 is negative 2. So let me replace what I know now. I know that this is 1, and this is negative 2, and then 1.5 minus pi over 2. I'm just going to do some distributing. Negative 2 times 1.5 is negative 3. A negative times a negative is a positive. 2 times pi over 2 is just pi. So if you do some quick subtraction or addition, you get negative 2 plus pi. You don't see that as the answer, but it's there. It's actually as pi minus 2, which is C. All right, so that's it for approximation. Let's move on to the next lesson. In this case, we're talking about an absolute maximum value for f. Okay, so the way that we did this in class by hand, and I'll show you again how to do this using Desmos. If you want to use that, that's fine. But by hand, we need to take the derivative of this function. So I'm going to do, d dx of the natural log of x over x. All right, now I'm going to use the quotient rule here. All right, and let me just pull up my derivative formula sheet. So that way we feel confident on this. All right, because I do have to take the derivative of the natural log of x, which you'll see here. The derivative of the natural log function is 1 over whatever your argument is times the derivative of that argument. So in this case, the argument is x. So it's 1 over x times the derivative of x, but that's just 1. So we just leave it like that, times the original denominator, which is x, minus the derivative of the denominator, which is 1, times the original numerator, all over the denominator squared. Okay? So if I clean this up, the derivative is going to be 1 minus the natural log of x over x squared. And you want to find critical points for this. And the way we found critical points is whatever makes our derivative of our function equal to 0 or undefined. Now, this is a rational function. So when I look at, I should say, the derivative is a rational function. So I'm thinking, okay, we could get undefined here, except when I look at the denominator says x squared. So there's no way to make that, I'm sorry, there is a way to make that become 0. It's just x equals 0. So that's one of them. And the other way is to make our numerator become 0. So set 1 minus the natural log of x equal to 0. So that's going to be 1 equals the natural log of x. All right, and actually let me write it like this. That'll help based on what we talked about in Algebra 2. All right, so if I swoop, this is e to the first power equals x. So e to the first power equals x. So those are my two possible values. So I plug those into the original function to see what happens. Now here's the problem about plugging in 0. When you plug in 0 to the original, you just get divided by 0. So that's not going to work. So really it comes down to what happens when I plug in x equals e. So I'm going to do f of e, which is the natural log of e, over e. All right, and the natural log of e is actually 1. So my absolute maximum value has a y value of 1 over e. So the answer is B. Now let me go to Desmos and show you what happens when you type in the original f of x function. So I'm going to type in the natural log of x over x. So the natural log of x over x. And if you look, you'll see that it's going to tell us where the maximum is. It's right here. Now you should notice that our x value is 2.718, which is approximately letter E, like we found. All right, but this question is not asking for the x value. It's asking for what's the absolute maximum value of our function, which whenever they ask that, they're asking for the y value. So the y value is 0.368, which is 1 over E 0.368. So those match for the y value. Okay, so that's how I did number 9. Let's go to number 10. Okay, number 10 says we want to find the value for k where g has a critical point at x equals 2/3. All right, so I need to find the derivative of this, right, to find my critical points. Again, product rule here. So that's going to be 2x times e to the kx power plus the derivative of the exponential function, this natural one, is just you copy it and then you do g prime of that power. All right, so watch this. You copy it, so e to the kx times what's the derivative of the power? The derivative of kx is just k. And don't forget, with our product rule, times the original first one, x squared. All right, so there's a lot going on here. I'll clean it up a little bit. So we get 2x times e to the kx power plus x squared times k. Actually, I'll put that in front. Kx squared times e to the kx power. Now, I'm going to set this equal to 0, and I'm going to do that by also factoring to solve. So I'm going to factor out an x and e to the kx. So x times e to the kx. That's factored out. I'm left with 2 plus kx, and that's equal to 0. Check to make sure by distributing and make sure you got the same stuff still. Yep, we're good. I'm going to set each of these equal to 0. All right. And then you'll see, like right now, I can't do anything about that, but it tells me that x is equal to 2/3. So if I replace these x's with 2/3, then I can solve for k. So 2/3 times e to the 2/3 k equals 0. 2 plus 2/3 k equals 0. And then I'm solving. So I'll do the one on the left first. Dividing both sides by 2/3 or multiplying by the reciprocal 3/2. Not going to do anything, just e to the 2/3 k equals 0. All right. So then I'm trying to figure out, my understanding here is that e to the first power is 0. So this 2/3 k must become 1 for that to be true. So 2/3 k equals 1. All right, so if I move the 2/3 over by multiplying by the reciprocal, I get k equals 3/2. All right, so that's one of my answers. Let's try the other one. Moving the 2 over here, I get -2, and multiplying by the reciprocal of 3/2, I get -3. So those are my two answer choices. Unfortunately, I have to only pick one. All right, and the only one that's here that corresponds to what I have is k equals -3, or answer choice A. So positive 3/2 would work, but I don't see it. That's why I picked A. All right, let's go to 11. We have a function that has the property of the derivative of that function is less than or equal to 3 for the values for x, that are between 1 and 8. It tells us that f of 5 is 6. Which of the following could be true? So here's how I did this. Just drew a quick sketch here. F of 5 is 6. So like there. So that's 5, 6. All right. They're telling us, okay, could f of 2 be 0? Well, if this is going to be a possibility that could work, then when I look at the derivative at x equals 2, it should be less than or equal to 3. And we can do that by finding the slope of that line, because that would be the slope of our derivative there. So if I find the slope there, that first one is going to be 6 minus 0 over 5 minus 2, just 6 divided by 3. The slope is 2. Is that slope less than or equal to 3? It is. So 1 works. Let's try the next one. 6 comma negative 2. So 6 comma negative 2 would be here. Again, if that would work, then when I find the derivative at that value, it should have a slope that's less than or equal to 3. So I'm going to do, this is 6 negative 2. So the slope for that one is going to be negative 2 minus 6 over 6 minus 5. So that's going to be negative 8 over 1, which is negative 8. Is that less than or equal to 3? It is. So that one works. Let's try the last one. 7/13. So that's way up here. 7/13. Finding that derivative, looking at the slope, when I connect those 2 points, I get 13 minus 6 over 7 minus 5, which is 7 over 2, which is 3.5. And unfortunately, 3.5 is not less than or equal to 3. So that one doesn't work. So only 1 and 2 are solutions that work. Okay, let's go to 12. All right, we have our function here where it gives us values for when I plug in 0 and 2, and they give us the derivative, how many values of x in the open interval 0, 2 satisfy the conclusion of the mean value theorem. So now, when it comes to the mean value theorem, all right, what this is saying, let me actually go to it real quick. In our notes, I think it's 4.4. Yep, there it is. So this is the slide from our notes on the mean value theorem. Remember, you can always GTS if you need to. But we're saying that there's some points in between these values of A and B, so some point in there, all right, or points, where that if you take the slope of the line that's tangent to the curve at those x values, it would be the same as the slope that connects those two endpoints, okay? So when I look at this one, right, if I'm looking at 12, if I find the slope of my two endpoints on 0, 2, that's going to be the y values, y over pi squared minus 1 over pi squared over 2 minus 0 which is 0 over 2, or the slope is 0. So if I can find any value where I find that the derivative would also be 0 at that point, then I know that it must make this mean value theorem true. So I'm going to set my derivative equal to 0. And I'm going to separate these. This one's pretty straightforward. You get -1. This one is a little bit trickier. All right, so I'm trying to figure out values for cosine that become 0. And when I think about my quadrantals, right, when I have my points up here at 0, 1, or at 0, -1, the cosine of those would be 0. So that's pi over 2, and that's 3 pi over 2. So I'm setting this pi over x right here. This pi over x must be equal to pi over 2 or 3 pi over 2 for this to work. So I'm going to set those two things right here. And you'll notice the pi's will go away. So this is going to be 1/2. And this one's going to be 3/2. So it looks like there's 3 that would work. But be careful. Here's that last check, because it has to be in the interval. Remember, the interval is 0 to 2. All right, so this one's not going to work because that's not in the interval 0 to 2. But 1/2 is in the interval 0 to 2, and 3/2 is also in the interval 0 to 2. So the answer would be there are 2 points that would satisfy the conclusion for the mean value theorem in this interval. All right? Okay, let's go to 13. Now, 13, very similar problem about the mean value theorem. All right? Again, if I go back to that slide, I'll go back to it again on 4.4. Oh, I'm sorry. That's the homework. Here we go. There it is. You'll notice that I'm looking for the slopes of the tangent line to be the same as that slope of the secant line that connects the endpoints. Okay? So I'm looking for those slopes to be the same. Now watch what that means in terms of this question. All right? So if you look at the endpoints, right, and the slopes are the same, I've got this one and I've got this one. All right, so that's x sub 1 and x sub 5. All right, so those are going to be my 2 answers. Now, I'm looking at C, but I also see x sub 1 and x sub 5 in letter D. Now, be careful here. I'm trying to get you to think that because x sub 3 is like in between those, that it should also work. But if you draw, I'll just use a different color. If you draw the tangent line there, the tangent line is going to be like this, which does not match that slope. So just be careful. They're just trying to trick you. So 13 is C. Okay, let's keep going to 14. All right. Now I'm going to go to just use decimals for this one. All right. But eventually, or essentially what I'm saying here for this one is if we're going to use the mean value theorem to look at these 4 functions between -3 and 3, we know it has to be continuous and differentiable, all right, between those in order for this to be true. So watch what happens when I graph these 4 in Desmos and I look at that interval. All right, so the first one is x to the 2/3 power. So x to the 2/3 power. I'm going to just type them all in first. Then I have the absolute value of x minus 1. Then I have x minus 2 over x minus 5. The last one is you flip that, x minus 5 over x minus 2. I'm going to go one at a time. Here's the first one. And remember, I'm focusing on -3 to 3. All right, so -3 to 3. Do I want to go one more? Sure. Okay, so here's -3 to 3. You'll notice that at 0, that this is not differentiable. Remember, that's that rough point or that curve there. All right, if you don't have a smooth value there, it's not going to be differentiable. So this is not going to work out because it's not differentiable in between there. Okay, let's look at this one. Same thing. Absolute value, your ears should be perking up here. You've got at x equals 1, you've got a point where our function is not differentiable. Let's try this one. Okay, this one looks okay. -3 to +3. It's continuous. I don't see any rough or curved spots here. It's all smooth. All right, so that looks like it's going to work. Let's just check the last one. And the last one, you can see we have an issue. We have a vertical asymptote at x equals 2. That's going to be a problem because it's not continuous. All right, so the answer is C. Let's go to 15. 15 gives us a function, and it says what value of x in the closed interval 0 to 5 does the instantaneous rate of change of f equal the average rate of change of f over that interval? All right, so same idea here. I need to find the slope of the endpoints here. So the interval is 0 to 5. So I'm going to plug in 0 and plug in 5. Plugging in 0 is pretty easy. You get negative 16. But when I plug in 5, might need to use a calculator here. I'm going to for sure. All right, so again, using Desmos or your phone for this one, we've got 125 minus, let's see, 5 squared is 25, so that's 50, and then plus 25 minus 16, so I get 84. I need to find the slope that connects these 2 points. So that's going to be, let me write down the points so you can see what my brain's doing. So those are the 2 points. So I have 84 minus negative 16 over 5 minus 0. That's 100 over 5, which is 20. So I'm trying to find values in this interval that are going to make this original function, the derivative of it, become 20, right? I'm looking for the same slope of 20 for my values in between, all right, for the tangent line. So I need to find the derivative. So f prime of x, which is d dx of x cubed minus 2x squared plus 5x minus 16. And once I find this, I need to set it equal to the slope of 20. That's 3x squared minus 4x plus 5, and that's equal to my slope of 20. All right, so I get 3x squared minus 4x, and I want to move that 20 to the other side with subtraction. So I get minus 15 equals 0. Now it's time to factor. You could use factors of a times c that add to b, like we've done many, many times. I'm just going to use some guess and check here. Factors of 15, of 5 and 3, or 1 and 15. What ends up happening is I use 3 and 5. That's going to give me 9x and 4x, and I want the 9x to be my negative and my 5x to be positive, because negative 9x plus 5x is negative 4x. So my 2 solutions here are going to be x equals negative 5/3 and positive 3. Again, it has to be in the interval. You'll notice that the only one that's in the interval between 0 and 5 is positive 3. The answer is D. Okay, 16. We're getting close, guys. 16 says, for which of the following intervals is our first derivative greater than 0 and our second derivative less than 0? Now, this is going back into kind of the middle lessons, and most of these lessons, or some of these lessons, I wasn't here because I was out for a few days. So hopefully you got a chance to watch the videos. Whenever I read this, I'll just write down what my brain is thinking. First derivative tells me if f of x is increasing or decreasing. Okay? The second derivative, right, the sign of that tells me, let me do this, sine of second derivative tells me if f of x is concave up or concave down. Okay? So in this case, it says our first derivative is greater than 0. So that means we're talking about increasing. And our second derivative is less than 0. So we're talking about concave down. So that's what I'm looking for here. All right? Well, I'm increasing from A to B, definitely increasing there, and from B to C. I'm decreasing from C to D, so I know C to D is not going to work. I have no idea what's happening in the hallway right now, but just bear with me. I'm trying to focus. I'm sorry. And then, so I have to narrow down between A and B and C, or maybe they'll both work. But I need concave down. Remember, concave down? Let me do concave down. Oh, man. Concave down is like a frown. So it'd be like this. And if you notice with my A to B, that's more concave up, where you can hold water, like hold a cup. So B to C is going to be my answer here. So 2 only. All right, so 16 is B. All right, 17. All right, we have the graph of f prime. You know what? I'm just going to pause here because it's too distracting to have music going on. All right, guys. So we're on number 17 here, and they give us the graph of f prime of x. That's one of those things that it might be trying to trick you here. So always make sure you know what you're looking at. Are you looking at the graph of the original function? Are you looking at the graph of the derivative? Make sure you know what you're looking at, okay? So when I look at the graph of the derivative of our f of x function, I'm always thinking about what that tells me. And remember, the sine of the first derivative will tell me if the function is increasing or decreasing. Okay, so if the sine of the first derivative is positive, that's going to be that the original function is increasing. If the sine of the first derivative is negative, then the original function is decreasing. So when I look here, I'm looking at I am increasing from -2 to 0, okay? And I'm decreasing from 0 to 2, okay? So when I look at my answer choices, looking for anything to match up with that, and it looks like f is, let's see, decreasing, increasing, which one do I got? Decreasing between, increasing from -2, there we go, it's B. Increasing from -2 to 0. So 17 is B. Let's go to 18. All right. So 18 says that we have the g of x function. We want to find on which of the following intervals is it decreasing. Now, I know you guys can go into Desmos, type this in, and just look to see where it's increasing or decreasing. But doing this the way we did it by hand was we want to find the critical points. So I want to find the derivative of this function first. Okay, so the derivative of a polynomial, we're just going to take each derivative by itself. That's going to be x squared plus 3x minus 70. And remember, the critical points are whatever makes this derivative equal to 0 or undefined. And this is a quadratic trinomial, so we have no issues about if it's defined or not, so we're good there. But I do want to set it equal to 0. And you'll notice if I set it equal to 0, I can factor this as x plus 10 and x minus 7. So my two critical points are -10 to 7. So what we did in our notes was we divided up our domain of -infinity to infinity into -infinity to -10, -10 to 7, and then 7 to infinity. All right? Made a quick little table. I don't really need to make like a full-on table, but I'm going to do the sine of f prime of x here, and that will be my conclusion on if it's increasing or decreasing, the original function that is. So I'm going to plug in -11, and personally, it's up to you. You can always go back to the original derivative that you found, but I think it's actually easier in this problem to go to the factored derivative one. So if I plug in -11, I get -1 times -18, which is a positive. So that means my f of x function is increasing. Let me write that actually out so that way if you're just reading this, so f of x is increasing. If I plug in 0 for the next one, I get a positive times a negative, which is a negative. So f of x is decreasing. If I plug in 8 or any number you want that's greater than 7, you'll get a positive times a positive, which is a positive. So f of x is increasing. So to answer this question, which of the following intervals is the function decreasing? The only one is between -10 and 7. So letter D. Again, you could do this by just plugging it into Desmos, plugging in the original function. Let's go to 19. All right, so 19, it says, here's the graph of the first derivative. Which of the following intervals is the f of x function decreasing? Again, we've done this now a couple of times, but if the sign of the first derivative is negative, so sine of f prime of x is negative, then f of x is decreasing. All right, so I'm looking for where is the curve here below 0. So that's going to be 0 to 2, 0 to 2, and then 4 to 6. All right, so my answer is E. All right, I'm going to do 2 more, and then we'll be done with this first part. Number 20 says, here's the function, and this is the derivative. On what interval is the function decreasing? So I'm going to do this just like I did before with number 18. Finding the critical points means whatever makes the derivative equal to 0 or undefined. There's no way to make this undefined because I can't make the denominator 0, because when I square x, it always becomes positive. Adding to 1 is still a positive. Squaring that is still a positive. So really it's just whatever makes the numerator equal to 0, which is x equals 0. So I'm going to split this up into negative infinity to 0 and 0 to infinity. All right, kind of make that little table again. So sine of f prime of x and our conclusion. So I'm going to plug in -1. That's a positive on top, to the derivative. And then a positive on the bottom, so that's going to be a positive. So f of x is increasing. If I plug in a +1, I get a negative sign, so f of x is decreasing. So it says, where is the function decreasing? That would be from 0 to infinity. So 20 is A. All right, one more. Now this one says that we have a function, and the derivative is essentially the difference of two squares. So when I did this problem, I just made up my own difference of two squares as x squared minus 4. So I have x minus 2, x plus 2. All right. So in terms of looking at my signs here, all right, I was looking at negative infinity. Let me write down my two numbers here. So x equals 2 and -2 for my critical points. So negative infinity to -2, -2 to 2, and 2 to infinity. All right. Again, I'm going to do the same thing. Make my little table, make the signs. I'm plugging into the derivative. Make sure you don't forget that you're always plugging back into the derivative. The sign of the derivative will tell you if your original function is increasing or decreasing. So I plug in -3. I get a negative times a negative, which is going to be a positive. So f of x is increasing. If I plug in 0, I got a negative times a positive, which is a negative. So f of x is decreasing. If I plug in +3, I get a positive times a positive, which is a positive. Okay, now this is saying which of these would be true. So all of the answers I noticed start off by saying decreasing. So I'm only looking at essentially highlighting and caring about the decreasing part, which is between -2 and 2. And I know I made up those numbers, but it's essentially between -a and +a. So when I'm looking at my answer choices, it's not for values for x being less than 0, all right, because that's going to have, for both of these, my decreasing was for -2 to 2. And then for this one, it's saying less than -2 and greater than +2, which I'm not going to be doing for that one. That's actually when it's increasing. So the only answer choice that makes sense is it's decreasing for values between -2 and 2 because our derivative of our function was negative, less than 0 for values between -2 and 2, which essentially is that step we did. All right, so 21 is A. All right, that concludes the first part. Make sure you tune in for the second part.